Okay, ladies and gentlemen, here we go. The periodic table and periodic All right. Now, I'm going to leave this to you and make sure that you read these vocab words. None of them are new. And that gets us right to this. You know, the atom is kind of a weird thing. When you think about it, what's in the nucleus? Protons that have, and neutrons, that have a positive charge. How come they're hanging around with each other? What should they be doing? But they're not. And that's because of some strong nuclear force, which is really cool stuff, but that's not what I want to talk about. You know what, if we knew that, that'd be great. The first energy level, nobody knows what force actually is. They're thinking we're getting close to knowing what it is. The first energy level holds how many electrons? Two electrons. Two electrons in the same electron cloud. Why are they hanging together? What should they be doing? They are repelling each other, but they're very attracted to the nucleus, so they hang around because they really like that nucleus. Okay, and then the second energy level holds how many electrons? 8 electrons. 8 electrons in 1s and 3p orbitals, yeah?
Yeah.
Okay, so while two things are going on. The electrons are attracted to the nucleus and they are repelled by each other. Okay, now let's say that there are 10 positive charges in the nucleus. 2, 4, 6, 8, 10. And 10 electrons in 2 energy levels. What atom would this be? It would be neon. All right. Tell me what we call these electrons in the outermost energy level. The valence electrons. Now we're going to define some other electrons, and those are core electrons. Core electrons are defined as any electrons that are not valence. Okay, so far so good?
Yep.
Okay. So now I want to describe what's happening to the core and the valence electrons. These core electrons are very close to the nucleus. They are penetrating the nucleus more than the valence electrons are. They are feeling a very strong tractor beam pull from the nucleus. Everybody understand that? Now these valence electrons, they're also feeling the attraction of the nucleus. But something is standing in their way. What's standing in their way? The core electrons. The core electrons are said to be shielding the valence electrons. They're hiding the delicious positive pull of the nucleus. Okay?
Question.
Yes?
Actually, I have 2 questions. First of all, if an electron hits a proton, does it become a neutron?
Yes, it does.
That's cool. And this second one I forgot.
Okay. But when you remember, let me know. Okay, so now we know what shielding is. That is the obscuring of the full charge of the nucleus by inner electrons. Now we're going to describe something called effective nuclear charge. It's abbreviated ZF. I call it ZAP. The effective nuclear charge is the positive charge experienced by an electron in a multi-electron atom. What the ZAP, or effective nuclear charge, takes into account is the shielding by the core electrons. So, any core electrons will reduce the nuclear charge acting on the valence. The effective nuclear charge can be simplified. It's not really like this, but for our purposes, we can simplify it to something that approximates this. The effective nuclear charge is equal to Z, the number of protons, minus S, which is the number of core electrons. I'll go through a couple examples. Yeah.
Okay, so hydrogen. Yeah, does it have like a valence electron or is it a core electron? Like,
Its valence electron is its core electron. It's still described as a valence electron because it's in the outermost energy shell. Has no core.
and what's stopping the electron from hitting the proton?
The fact that it's moving, it has an acceleration because it has a velocity. It's always changing direction, it's moving within the electron cloud, so it's accelerating.
What causes it to like accelerate constantly?
Just a changing in velocity, I believe.
Okay.
You know, the changing in direction.
Oh, that's it.
Okay. All right. Now, the positive charge, ZAF, felt by the outer electrons is always less than the full nuclear charge because of this pesky core. Okay, here's an example. Let's take sodium. Got it? Sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. Am I correct? Yes,
Yeah.
I am. Tell me, what electron is the valence electron in this electron configuration? The 3s1. So we have 11 protons in the nucleus. Our first energy level holds 2 electrons. Our third energy level holds 8 electrons. And then our second is 8, and our third has that one last electron. Is that correct?
Yep.
This is the valence, these are core. So the ZAF for sodium is the 11 protons minus the 10 core electrons equals an effective nuclear charge of +1. That means this electron is feeling a +1 attraction to the nucleus because of the shielding of the core. Now look at sodium on the periodic table. See it?
Yeah.
Okay. All right. Now, do we see sulfur down there? Down the period, correct? Sulfur has how many protons? 16 protons. The neutral atom has 2 electrons in the first, 8 in the second, and 6 in the third. Is that correct? Okay. Its effective nuclear charge is 16 protons minus the same 10 core electrons is a +6 effective nuclear charge. What this is saying is that sulfur valence electron feels a stronger attraction for the nucleus than sodium stuff. Does that make sense? Yes, because we know that sodium tends to form a +1 ion. Nothing's holding that one electron on there very strongly. That nucleus is like, yeah, see you later. However, sulfur holds on to its 6 electrons and tries to find 2 more, doesn't it? Okay, are we good with effective nuclear charge? Yep, moving on.
So does that say how reactive it is?
Kind of. This is the basis for all of the trends that we want to talk about. And the trends that we want to talk about do determine reactivity. Okay, we talked about electron configuration yesterday. I want you to know 2 of the more famous electron configuration anomalies, okay, oddities, that occur. The most famous ones are chromium and copper. Okay, we talked yesterday, there's 2 ways to write an electron configuration. There is this style, which we don't use much, and that is just in order of energy level. We like to use in order of filling. So we would write copper as argon, expectedly, 4s2 fills before the 3d9. That's what you would expect the electron configuration to be. Turns out the electron configuration is 4s1. It takes one of these electrons and moves it to complete the d block orbitals. Likewise, chromium does the same thing. It ends up being 4s13d5. That's just some oddity for you. I'm not going to test you on it, and I don't think AP is either. Okay, what's coming up next is by far the most important part of this chapter. If you are starting to doze off, now's the time to like poke yourself right in the eye. There you go. Now you're awake. Thank you very much. While it is important, we will talk about atomic radius. We'll talk about metallic, non-metallic character and electron affinity. By far, the most important thing that we need to talk about is ionization energy. First of all, to define it, ionization energy is the energy required to remove an electron from an atom. The energy required to remove an electron from an atom. If I have a sodium atom, I need to add energy, there's my energy in kilojoules, in order to pluck one of its electrons, leaving it positively charged, away from the atom. This is called the first ionization energy. Could I take more electrons from it? Yep. It started out with 11, I took 1. The second ionization energy would take another electron away from it, and that would be the second ionization energy. I could go until I took all of the electrons away from the atom. Primarily, we'll be talking about the first, second, third ionization energy. The ionization energy increases for successive electrons. What that means is the first ionization energy is less than the second ionization energy. Why is that so?
Because there's a meter jump into it.
Well, here's still 11 protons. So 11 protons. Now, sodium, you have fewer electrons. So those few electrons are being incredibly drawn to the nucleus. So the more you take away, the bigger the imbalance between positive and negative charge. Okay. The charge, the things that make a difference to the attraction an electron has for the nucleus is this: the charge on the nucleus. The more protons there are in the nucleus, the more positively charged the nucleus, the more strongly attracted the electrons are to it. The distance of the electron from the nucleus. If you have a valence electron in a high energy level, let's say period 6 or 7, that attraction is very slight because there's a really far away from the nucleus. An electron close to the nucleus will be more strongly attracted to the nucleus than one further away. And it also depends on the number of electrons between the outer electrons and the nucleus. What do we call those electrons? The core electrons, the core electrons. Okay, so let's look at this. Let's start out with sodium. Sodium has the electron configuration 1s2, 2s2, 2p6, 3s1. This we have determined is the valence electron, is that correct?
Yes.
These are the core electrons. Okay. The energy needed to take the neutral atom and take away one electron, the first ionization energy, is 496 kilojoules per mole. The second ionization energy, that would take the sodium ion, 1s2, 2s2, 2p6, that ionization energy is 4,560 kilojoules per mole. Why did it go up so high?
Because of
Plus
the
no
attraction.
distance.
It's close to the
Why?
closer to the
I broke into the core electrons, didn't I? I had to snatch an electron from the core. When I took an electron, I took this one.
Because it's more,
It's feeling a very strong attraction, okay, we still have 11 protons here,
Right.
and this had 10 electrons when I started, and I took one, so it had 9 when I was done. It really is held tightly. So it takes a bunch of energy. The lesson I want you to learn from this is when you empty the valence electrons, it takes a tremendous amount of energy to break in and steal a core electron. Got it? Now, let's look at magnesium. Magnesium, when it is a neutral atom, is 1s2, 2s2, 2p6, 3s2. The first ionization energy is 738 kilojoules per mole. That takes this electron right out in the valence electron and leaves magnesium as a +1 ion. The second ionization energy, taking a second electron away from it, leaves magnesium with a +2 charge and empties the valence electron. You'll notice it's a doubling here. This was times 10 when we broke into the core. We just took one valence and the other valence. When we get into the core to magnesium and try to take one of these electrons, the ionization energy just scoots way up there because we've broken into the core. So far, so good? Okay. Everything's damn delicious. We get this until we come to this thing. What is this? It is an ionization energy chart. We're talking about the first ionization energy, the energy needed to pull the first electron off of a neutral atom. Let's start, so this is kilojoules per mole. This is atomic number. Let's look here, and starting with the second period, here's lithium, there's beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Got it? Okay, I would like to talk about lithium first. Lithium has the electron configuration 1s2, 2s1. It takes 500 kilojoules to take away this electron. Okay, beryllium, 1s2, 2s2. It takes more energy to take away beryllium's first electron. Why? It has a stronger pull. Why does it have a stronger pull? It has more protons. Another way to say that, it is a greater effective nuclear charge, correct? The attraction of these valence electrons for the nucleus is greater than this valence electron for lithium's.
So why is helium higher than fluorine?
Okay, let me finish this and I'll be glad to answer your question. Okay, now here's something weird. Boron's electron configuration, 1s2, 2s2, 2p1, the ionization energy actually went down.
So is that how big the atom is?
Yes, it has to do with how far away and the energy level of this P is. Remember, S orbitals penetrate closer to the nucleus than P does. Okay, that means this is more loosely held than this. So the ionization energy goes down a little bit. So now we're at carbon, 1s2, 2s2, 2p2, a little rise. Nitrogen is 1s2, 2s2, 2p3, rises again. Then we have another weirdo, oxygen, 1s2, 2s2, 2p4. Why does it go down again? Well, let's just look at the orbital filling notation of the P only. There are 3 2p orbitals. Okay, so we filled them like this, and we finally have a paired sequence. What are those 2 electrons doing to each other? What are those 2 electrons doing to each other?
They're spinning in those directions.
but they are still two negative charges that are, they're repelling each other. So this one was kind of voted off the island. Go ahead, go ahead and take it. Yeah. They are voted off the island, so the electronegativity, the first ionization energy goes down a little bit. Now it goes up again for fluorine, and of course, neon has a noble gas configuration. It has the highest ionization energy. Okay. Now to answer the question about hydrogen, why is its ionization energy the tippy top?
Oh, because it's
It's 1s2, correct? The s orbital is very, very close to the nucleus, and it feels there's no shielding at all. So it feels the full nuclear charge. So they're very, very closely held. Now, some observations we've made about ionization energy are this. Ionization energy increases for successive electrons. That means the first ionization energy is less than the second, less than the third. Generally, ionization energies tend to increase across a period, except for those weirdness that we saw. I'm sorry, this was not generally, this is absolutely. Ionization energy decreases with increasing atomic number within a group. What does that mean? Let's look at group 14. The ionization energy as you go down group 14 decreases. Why is that? They're farther away. They're farther away. Okay, now I want to talk about electron affinity for 32 seconds. And the reason why I only want to spend 32 seconds on it is because ionization energy is hugely important. And I think right this moment in time, y'all get it, fine. Everything's good, we understand what's going on. I need to define electron affinity, and a lot of times when I start talking about it in depth, kids get kind of confused, and it's not worth the confusing you because you understand ionization energy. Let's define electron affinity as the energy change associated with adding an electron. Ionization energy, removing. Electron affinity, adding. All I would like you to know is the trend. Electron affinity increases across a period, becomes less negative, and it decreases as you go down. Done. Let's talk about atomic radius. Radius we can think of as size. Atomic radius in absolute terms is half the distance between the radii of a covalently bonded molecule. Here's the periodic trend. As you go across the period, it gets smaller. Why?
Just remember radius decreases across the period.
Back here. Let's look here. Are these two in the same period?
Yes.
Yes, they are. What is the
It's bigger.
what is the effective nuclear charge of sodium? Sulfur. Which valence electrons are feeling a stronger pull towards the nucleus? Sulfur are. If they're being drawn closer, the radius would be smaller. So as you go across a period, the atomic radius decreases. Now, as you go down a group, the size increases. Does that make sense? Yeah, because you're adding energy levels. So if you were in the third period, you would have the nucleus and 3 energy levels. If you were in the fifth period, you would have the nucleus and 5 energy levels. Of course, this would be bigger than this. Now let's talk about ionic radii, and that's the radius of an ion. Okay, let's talk about sodium. When sodium is neutral, it has 11 protons, it has 11 electrons. When sodium is an ion, It has 11 protons and 10 electrons. Is a sodium ion bigger or smaller than a sodium atom? Smaller is correct because these 10 electrons are feeling an 11 proton pull. So they get smaller. You know what? Here's a baby way to think about this. When you have a cation, it goes on a diet. It loses an electron and it gets smaller. When you go on a diet, you go down a size. An anion, let's take sulfur. Okay, we have sulfur, and when it is neutral, 16 positive, 16 negative. When it is an ion, 16 positive and 18 negative. It's bigger. It's just bigger. It's gained something, didn't it? So it went up a size. There we go. All right, now let's have a term, isoelectric. Remember I said that sodium ion had the electron configuration 1s2, 2s2, 2p6 because it got rid of its 3s1 electron. It is isoelectric with neon, 1s2, 2s2, 2p6. So sodium ion has 11 positives and 10 negatives. Neon has 10 positives, 10 negatives. It's isoelectric because the number of electrons are the same. Almost done, and you've done a very nice job staying awake. I appreciate it. Electronegativity is the ability of an atom in a molecule to attract electrons to itself. So here we have hydrogen that has one valence electron, and when it's covalently bonded, it shares that one valence electron, let's say with fluorine. Remember Lewis dot diagrams?
Yes, I know.
Now, fluorine does not share well. Fluorine burgles, it tries to take that electron closer to it. It is very electronegative. It is the most electronegative atom on the periodic table. Why? It's just one shy of a noble gas configuration, and it's just trying as hard as it can to get that one electron. What this does is make a polar molecule. Remember that part too. Okay, why is fluorine the most electronegative? Its Zeph for fluorine is 9 minus, how many core electrons will it have? Well, I don't know. Let's do this. 1s2, 2s, yep, 2s2, 2p5. How many valence electrons does it have? 7. So its core. What do you notice about Zeph? Same as the number of valence electrons. Got this? Zeph is the same as the number. Oh, yeah. Okay, so it's feeling a huge attraction to the nucleus. Not only is it tightening up, it's trying to attract another. Francium has the least. Francium has one valence electron. Its one valence electron is way, way out there. How many core electrons are there? 86 core electrons. It is so shielded from the 86 protons that it feels absolutely, it's just like, yep, really? Later.
And that's why it wants to.
And that's why it, yes, so reactive.
Because it
Yep.
gives it away very.
It's just a
Yep.
leech.
Yep.